Hello, and welcome back to The Complete History of Science. Series 2, Episode 3, The Origins and Development of Optics. From around the 5th century BC, the Greek-speaking world around the Mediterranean was a hive of intellectual activity. This was an incredibly exciting time, and the Greeks made huge intellectual strides in many fields: literature, political philosophy, mathematics, history, architecture. Their contributions would largely determine how these fields developed in the Western world. Likewise, and of interest to us, Greeks were also responsible for most of the major scientific developments in the ancient world, and many new scientific fields first appeared here. We've already discussed in this podcast some of the reasons this happened, which naturally are very complex and compel us to make generalizations about complicated historical forces. Nevertheless, I think we can at least look at some of the surface reasons this happened. And I believe this is still very valuable because it helps us to understand who the ancient Greeks were and how they became interested in science. Foremost of these reasons is that the Greeks possessed an insatiable curiosity about the world. They would ask questions about everything. Some of these were very big, like why do things change? What is it to live a good life? What is beauty? But more importantly, I think, in the growth of science, they also asked more modest questions. Things like, what is an eclipse? How large is the world? Or, if you're Aristotle, how big is an elephant's gallbladder? Some of these questions would have very clear answers, which the Greeks found almost immediately, while others would not be answered for centuries, if at all. What this second set of questions also have in common is that they are questions about the natural world. The Greeks asked questions which would now be familiar to any parent with a child, and I think this is because they spring naturally from the human desire to learn about and understand our everyday experiences. One of the questions which most perplexed the ancient Greeks is a question which is very immediate to our experience and can be stated very simply, but ultimately turned out to be incredibly difficult to answer. And that was, how do we see? This question would spurn the development of the field of optics, which became one of the richest scientific areas in the ancient world. While we now think of optics as the study of light, this was certainly not the case in its early history. Indeed, many of these early thinkers didn't seem to appreciate the existence of light as an abstract quantity. Instead, early Greek optics was most keenly interested in the study of visual perception. The ancient Greeks came up with many theories to explain this. However, they can be broadly divided into two distinct camps. The first and earliest of these theories has its origin in the work of Empedocles, who was active in Sicily around the 5th century BC. We've discussed Empedocles before, and his major scientific contribution was in demonstrating that air had some material substance, rather than being empty space. His theory of vision, however, is rather bizarre, because Empedocles, and there's no easy way to say this, believed that vision was a consequence of light being emitted from the eye. Now, to be entirely fair, this may be misleading, because Empedocles didn't use the word light, and like his contemporaries, didn't seem to have a good understanding of what light was. Instead, he used a term which is usually translated as the visual fire. The idea that Empedocles believed this derives from a passage where he likened the eye to a lantern searching outwards on a stormy night. Nevertheless, this theory, which came to be known as the extramission theory of vision, would have a long history in the field of early optics. In the main, it suggests that vision is due to some substance, though not necessarily light, which is emitted from the eye. However, even if we accept that these thinkers didn't mean that this substance was light, it's still a difficult idea to defend. Fortunately, one of the key attributes of Greek philosophy was that ideas were really universally accepted. Other thinkers during this period adopted the opposing view, which was that vision was due to some substance entering the eye, known as the intromission theory of vision. This theory was favoured by the group of philosophers known as the atomists, who we met previously in the episode on Aristotle. The atomists' primary belief was that the universe was composed of fundamental, indivisible particles known as atoms, and all of their other theories derive from this central idea. For example, one of these atomists, Epicurus, used this idea to give his own theory of vision. Epicurus suggested that vision was the consequence of particles, which are continuously being emitted by the surface of objects. These particles were not light, but instead the surface atoms of the objects, and so vision was a consequence of an outer membrane of atoms being continually shed by the object and entering the eye. However, this theory has some very obvious problems. For example, it implies that objects should be constantly diminishing in size. It also, like the early extramission theory, fails to really grasp the nature and role of light in vision. And this failure is clear if we ask one very simple, related question. Why is it we can only see objects during the daylight or in the presence of a light source? The first philosopher to attempt to resolve this problem was Plato, who had his own theory of vision, combining aspects of intromission and extramission theories. He proposed that daylight coalesced with the visual fire from the eye, which then formed a single, homogeneous beam, which further combined with some emanation coming from the visible object. As I think is clear though, this theory is fairly convoluted, and the details are complex, but it is notable because Plato was at least attempting to answer these very obvious questions. However, as usual in the ancient world, the most influential philosophical account was given by Aristotle. Aristotle was highly critical of earlier theories, and he put it quite bluntly, saying, "Vision is neither fire, nor in general any body, nor an emanation from any body." Aristotle instead imagined that there was a single homogeneous medium between the eye and the object. This medium was a sort of ether which was contained in air and other transparent bodies, and its function was to transmit colour from the object to the eye. Aristotle explained the need of a light source by suggesting that this medium was only transparent in the presence of light. So, in this view, the medium switched from being opaque to transparent in an instant, implying that light travelled infinitely fast. Of course, Aristotle's theory of vision, like all of these early theories, is a long way from our current understanding. By the time of Aristotle's death at the end of the 4th century BC, there were a multitude of theories of vision, but they were all highly speculative and at times completely bewildering. However, another strand of optics was developing separately from these philosophical investigations. This other thread would evolve into a distinct field in its own right, but would have its roots in another passion of the ancient Greeks: mathematics. The first tentative steps towards this more quantitative approach were actually taken by Aristotle himself. In his book on meteorology, Aristotle attempts to explain the formation of rainbows, using the idea that rainbows result from the reflection of sunlight by water droplets. To explain this, Aristotle constructed complex geometric diagrams, which featured light travelling from the sun in straight lines, an early version of a ray diagram. This construction is both intriguing and important because it anticipated one of the key developments in early optics. This development, however, was not primarily due to Aristotle, but started in earnest with the work of another of the great figures of the period, Euclid. Euclid has been mentioned briefly in passing on this podcast before, as the author of one of the great books of antiquity, the Elements, which would have an enormous influence on the field of geometry for the next 2,000 years. However, Euclid's other work, Optica, written around 300 BC, is now mostly forgotten and only survives in part. Nevertheless, Optica is an important work, primarily because Euclid breaks entirely from the earlier philosophical tradition of optics and excludes any discussion of the visual theories which preceded it. Instead, it focuses on a mathematical approach to the subject, applying his geometrical knowledge to the problem of vision. Optica is laid out like the Elements, where Euclid proceeds from several postulates, which he takes to be self-evident, in order to prove various theorems. Euclid's analysis relies on the idea of the visual cone. His first postulate assumes that visual rays move outwards from the eye in straight lines. These move in all directions, and so the collection of these rays form a cone. This assumption allows him to transform questions about optics into geometrical problems, and Optica then is primarily concerned with the spatial relationship between the observer and the objects. So, for example, Euclid examines how various objects look as the distance to them is varied, or as the angle of the object is slanted. In other words, Optica was offering a theory of visual perspective. Unfortunately, there are flaws and limits with Euclid's approach. For example, in one of his postulates, he states that the apparent size of an object is proportional to its angular size in the visual cone. The problem with this, however, is relatively straightforward. If we have two objects lying at different distances, we know immediately which is further away. And this is true even if they appear to us to have the same apparent size. Euclid's geometrical theory is limited because it has no clear way to deal with depth perception. It should also be noted that Euclid's analysis is based on the idea of the extramission theory of light. And while it's true that Euclid never explicitly discusses this idea, it's clear from his geometrical constructions that the visual cone is emitted from the eye towards the object, and all of his descriptions and diagrams endorse this idea. Of course, we could argue that Euclid's mathematical models were just that, mathematical models. But these models were also extremely lacking in the context of many questions we might reasonably ask around vision, not only around depth perception, but also the role of light or colour. Euclid's legacy, then, is twofold, because while the application of geometry to optics was an important milestone, it also demonstrates that no purely geometric theory can fully deal with all of the questions we have around vision. If we aim to answer the seemingly simple question, how do we see, it's clear that the theory would have to include a description of the physical and perhaps even psychological aspects of vision. Euclid's impact in mathematical optics, however, was great, and he clearly influenced the next substantial figure in this field, Hero of Alexandria. Hero was working in around the mid-1st century AD, and may be considered more of an engineer than a scientist, perhaps most famous for his many legendary inventions. These include a proto-steam engine, an early thermometer, and the world's first vending machine, which dispensed a set amount of water when a coin was inserted. Hero enters the story here, however, because he also wrote a treatise on catoptrics, which is the study of the reflection of light. The study of reflection had largely been ignored by Euclid in his original work Optica, and though he supposedly dealt with it in a separate work, it's of dubious authorship. Like Euclid, Hero wasn't interested in debating the reasons we see, but instead is much more clearly interested in applications. In his book, Hero gives perhaps the earliest statement of the law of reflection, saying that the angle of incidence of a ray on a plane mirror is equal to the angle of reflection. He succeeds in proving this mathematically by assuming the ray will take the shortest path between points. Like all of Hero's work, it is also preoccupied with applications, and he investigates the arrangement of mirrors, often for novelty purposes, and to produce various funhouse-style type optical effects. However, Euclid and Hero's contributions are ultimately footnotes in the history of optics, as they were completely eclipsed by another of the great figures of antiquity, Claudius Ptolemy. Interestingly, Ptolemy, like Euclid and Hero, worked in Alexandria, which was by now Roman Egypt. As with his writing on astronomy, Ptolemy sets out to build on the work of his predecessors and encapsulate the field as it stood at the end of the 1st century AD. In large part, he was successful in this endeavour, and he hugely expanded upon the geometrical work of Euclid, combining it with his own physical interpretation of vision. Ptolemy's triumph was in recognising the limitations of any one approach to optics, and so was the first person to attempt to merge mathematical optics with the more philosophical tradition. Ptolemy's mathematical analysis, like Euclid's, relies on the extramission theory of vision, where visual rays moving out from the eye form a visual cone. However, Ptolemy clearly believes that these rays have some physical basis, and we can't dismiss them as simply a mathematical model. And that's because, unlike Euclid, Ptolemy was actually interested in answering the central question of Greek optics, that is, how do we actually see? His answer to this is to assume that the visual rays must be reflected back towards the eye, taking with them visual information such as colour, shape, etc. This physical approach allows Ptolemy to resolve the problem of depth perception, which he clearly recognises in Euclid's work. His suggestion is that these visual rays sense the distance travelled, and hence contain information about the distance to the object. Naturally, this theory, like the philosophical theories which preceded it, lack a clear evidence base. Similarly, Ptolemy's geometrical theory, relying on the extramission of the visual cone, is difficult to reconcile with a theory of vision. One major objection is how do the rays reaching an object know where to return to? Ptolemy also recognised that light was necessary for vision, but couldn't say more than that, and it's not clear to me at least how light enters into Ptolemy's theory. Ptolemy's work represents the height of Greek optics, but also, in essence, its failure, because he fails to give a satisfying answer to the question of vision. Despite these shortcomings, Ptolemy's optics is still a great achievement, and represents an expansion of the field of optics beyond simply the study of visual perception. This is because, beyond Ptolemy's ideas around vision, he also conducts a detailed analysis of two of the most important optical phenomena known to the ancients, reflection and refraction. Whilst Ptolemy can't claim credit for the law of reflection, which had been previously stated by Hero of Alexandria, and likely known long before, Ptolemy's contribution was to propose a simple experiment intended to verify this law. Ptolemy's actual description of the experiment is quite complex, but I think the following at least captures the essence of what Ptolemy was suggesting. He starts with a circular bronze disc, divided into 1-degree increments. This is then aligned to a sighting device, known as a diopter, which has the ability to move along the edge of the disc and rotate around the centre. Along this centre lies a mirror, extending across the diameter of the disc. Ptolemy then places a coloured peg at various increments along the edge of the disc. To check the law of reflection, he then views these pegs through the dioptra. Ptolemy tells us that these pegs are only visible when the dioptra is set to be the same angle from the centre as the pegs. While this is a relatively simple experiment, I think it's a remarkable achievement. Thus far in our story, experiments have been virtually unknown. Some earlier figures, such as Aristotle, had explicitly dismissed the idea we should seek knowledge through what he called artificial situations. And although we have some prior examples which we might be tempted to characterise as experiment, I think they're missing something in terms of the scientific rigour which Ptolemy displays here. Ptolemy's work in this area is methodical, setting up a hypothesis, taking a series of measurements, changing one variable while measuring the other. In other words, Ptolemy is conducting an experiment using something which very much looks like the scientific method. And this wasn't the only example of Ptolemy's experimentation, because he also adapted this experiment to investigate refraction. Refraction, as a phenomena, was known long before Ptolemy. An oar, for example, set in a river, appears to bend. Hero of Alexandria also gave some account of refraction, noting that the visual ray, or light, bends as it moves between mediums. Ptolemy, however, applies a more recognisably scientific approach to examine refraction. His apparatus is similar to his reflection experiment, and he again uses the bronze disc with angular markings and the dioptra. However, instead of the mirror, he submerges half the bronze disc into water. By adjusting the position of the dioptra in angles of 10 degrees, he made measurements of the angle of refraction by judging the sighting of a marker which was placed in the water. Again, I'm greatly simplifying the details of this experiment, but I believe Ptolemy's methods should allow for accurate measurements of the angle of refraction. Indeed, his actual values are very close to what the modern accepted values would be, differing by less than 2 to 3 degrees. However, somewhat disappointingly, it's likely that these discrepancies don't result from experimental error, but rather that Ptolemy rounded these values based on his expectations. This is because his values for the refracted angle increase by exactly half a degree less for every increment, and it's probable he fixed his values to fit this perceived pattern. This is unfortunate because Ptolemy's experiment was capable of being extremely accurate, and this fudging of the data is something of a blot on his legacy. Nevertheless, Ptolemy's work in this area was still a great achievement, and I think that Ptolemy deserves recognition for being amongst the first scientists to conduct rigorous experiments. Ptolemy, dare I say, is a slightly maligned character in the history of science, but the more I learn about his work, the more I respect him and his accomplishments. Unlike most other scholars of antiquity, his work contains an awareness of the importance of both the mathematical aspects and the more qualitative or philosophical aspects of studying the natural world, and there's a nice synthesis of this in his work. For example, he frequently sees the practical applications of his more abstract ideas, and this is nicely demonstrated in his work on refraction. Ptolemy, as we know, was one of the greatest mathematical astronomers of antiquity, and so he realised that refraction would have an important effect on astronomical observations. Simply put, Ptolemy realised that the Earth was surrounded by a blanket of air which is denser than the material above it. He then recognised that this change in density will cause refraction to occur, meaning objects were not actually at their perceived position. Likewise, he knew that this effect was least if we look directly up, that is, along the zenith line, and the effect will be greater the further we move away from the zenith. Unfortunately, Ptolemy had to conclude that in his present state of knowledge, he would be unable to determine the amount of refraction which would occur, knowing so little about the depth of the atmosphere and also what came above it. This part of his optics, though, nevertheless provides a nice link between his astronomical and optical interests. However, in terms of his legacy, it's remarkable how differently these contributions would be felt in posterity. While his astronomical work, the Almagest, would become one of the most lauded and widely known books in antiquity, his optics would attract little interest in its day and be mostly forgotten until its legacy would be saved by a few Arabic scholars around 800 years later. These scholars would actually take Ptolemy's work as a jumping-off point, and they would ultimately settle the question which had plagued antique optics, the question of how we see. However, we'll leave this story for another day. This has been a much longer episode than I originally intended, taking in optics over roughly the first 5 centuries. In the next episode, we'll take a step sideways to explore the origins of another of the great scientific fields in antiquity: medicine.